go. Okay, so first up are announcements, and I just wanted to show everyone, I just, right before the lecture, I posted a new announcement regarding the midterm. So the midterm has been set on the 29th of October, which is during class, or at least at class time of the class. And the setup is going to be fairly simple. The examination itself will be released online through the Blackboard system. You have an hour and a half to complete your answers, and then you upload the written answers through the Blackboard system again, just like you've done with your problem sets. The exact details, including the cover sheet, will be released in a few days before the actual midterm. And the topics that we'll cover are the first three topics that we've gone through. So electrostatics, magnetostatics, or in general, just the static electromagnetic fields. And then finally, what we've been doing in the past few weeks is solutions in electromagnetism. So these are the different types of ways in order to solve for the potential or for the vector and scalar potentials to get the electromagnetic fields. Okay, as I said before, we will be giving you a set of equations during the examination, so you can go through those without having to memorize things like vector identities. I will also, by the end of this week, probably over the weekend, I'll release a set of notes that cover the first few all the way up to the midterm, including all the maths and the physics that we've covered. Okay, and so you can take that as a revision tool to prepare for the midterms. Okay, are there any questions or comments about this? So Wang Zhehyang is asking, do we need to open the camera? So that's something that we are trying to figure out how to best do that. We haven't fully settled on the best way. My own personal inclination is that I do think there has to be a level of trust in you as well. We're a fairly large class. We're like 80 something. I don't know how feasible it is to have everyone's webcam on and so on. But we'll try to find a way to make it not too cumbersome for everyone, so easy to do, with a little bit of trust in everyone, but also at least have to make sure that this won't be just a that it's not too easy to cheat either. Again, my personal feeling about these things is you're all over 18, you're all adults. If you really feel the need to cheat on examinations, then personally, it's something. I mean, it's something that you have to live with the consequences for yourself. Okay, I don't think you study physics just to get your degree. I hope that you study physics because you enjoy it. You actually want to learn something. And so the midterm is just a way for you to test what I consider to be the bulk of the knowledge that you're going to need to fully understand, but also be able to solve problems in electromagnetism. So yeah, so it's up to you to do it. So it's going to be something that I think hopefully will strike a balance between putting the responsibility with you as a responsible learner and with practical feasibility. So Jason is asking whether I can release a set of equations few days before. So indeed, that's what I'm saying. Like in the week, a few days before the actual examination, I will release the so-called cover sheet. So this is just a set of instructions, set of rules, but also, you know, the equation sheets and everything. So that will be released a few days before the examination. Okay. Any other questions about the midterm? Going once, going twice. Okay, in that case, let's just go to the main part of the lecture for today. Oops. So let's do the screen share. Okay, so let's get started. And let's go to this page. So let's start with a recap where we left off from last time. So last time we looked at another way of solving the Poisson equation. We actually looked at two ways, right? One is how to use the multipole expansion so far, and in particular, you know, kind of specific examples. So what if I have a particular, you know, charge density distribution that you're given, and then you're asked, okay, well, what if I stand far away from the source? What are the leading contributions? And those typically reduce to an integral, which is over R. Well, okay, let me write it down. So the multipole expansion. Right? So we're talking about some phi that you want to solve. And so this is rho minus R prime dv prime. And so again, I can do the integral over, you know, several terms. Well, let me just do it this way. It's easier to just write. So this could be rho over P in, this is just the sum in cos theta dv prime. And so, well, this is an exact, and then of course I can take the first few, you know, I can take the first few terms. So this is rho, and this would be P, and actually this is not complete. This should be, okay, let's rewrite this. Okay, so this should be 1 over R, the sum, and from 0 to infinity, the integral of rho Pn, which is a function of cosine theta, and you got R prime over R to the power n, and all integrated with respect to dv, right? Again, so this is an integral inside the distribution. So here we get, for example, R naught cosine theta dv plus 1 over R integral. This is R prime over R P1 cosine theta rho dv, and so on. And so here we're simply doing an expansion, and we keep, you know, adding to this depending on which are the lowest order, or we take the next leading order just to get our approximation. Okay, and so please quick second to turn off something. Excuse me. Okay. So the other thing that we looked at last time is we started to make our headway on the separation of variables. And here what we did is, assuming that we want to solve the Poisson equation, right? So, sorry, okay, it doesn't matter actually. We can do the Laplace equation or the Poisson equation. Then what we did is, under the assumption that phi can be separated into a function of x, y, and z, like this. Okay, so what we have here is then just a set of equations, but now that the separate contribution for x, y, and z can be seen. And we realized and we showed that instead of having one partial differential equation, we actually end up with 3 ordinary differential equations that then are related through another equation of their respective constants. So in this case, we end up with x prime prime as a function of x. Well, okay, we'll do it this way. So x prime prime over x equals n squared, and then we get y prime prime over y equals m squared, and then we get z prime prime over z equals l squared. And these are constants. These n, m, and l's are constants that are related through l squared plus m squared plus n squared equals to 0. Okay, so indeed we can see that starting from a partial differential equation over here, by assuming separation of variable, we can turn this into 3 ordinary differential equations, but that the constants, the separation constants, are related through a particular solution. Okay, so last time we showed the actual solutions to these equations over here, which you can write in terms of exponentials, or you can write them in terms of cosines and sines. And so here, let's take a specific look at the equations. And now let's see if we can really get to a solution. And so for that, I actually want to turn into 2 dimensions, not because of that it's fundamentally different, but just it would save me a lot of writing, and we can go through a particular example more quickly. So let's take a look at the Cartesian coordinates. Again, so we take a look at the Cartesian coordinates, but in 2D. And so in 2 dimensions, we actually have the following solutions. So the solutions in the form, and here I can write x double prime equals, and I'm just going to call this lambda x, okay, but lambda is a constant now, and y double prime equals minus lambda squared y. And so this is basically, instead of now naming this n squared and m squared, because I know the relationship that that the squares of these constants need to add up to 0, I can simply start writing now here L squared and here minus L squared, or lambda squared, where in this case lambda squared is bigger than 0. Okay. Now, of course, the full solution is given by phi equals x as a function of small x and big Y as a function of small y. Now, taking a look at these 2 equations over here, so we've got the 2 ordinary differential equations, I can immediately write down these solutions. So here I can now write, and I'm just going to add in some constants, but I can write A equals the hyperbolic cosine lambda x plus b, and the hyperbolic sign, lambda x, times c, the regular cosine, lambda x, plus d, the regular sine, lambda x. Or, of course, I can write them in terms of exponentials. So let me write a prime, e lambda x, plus b prime, e minus lambda x, times c prime, e I lambda x, plus d prime, e minus I lambda x, sorry, lambda y. Okay, so in the two-dimensional case, it's relatively straightforward. We've got our two ordinary differential equations so that x and y can be written of the following form. Okay, I see that someone's trying to point out that indeed these should be y's. Done. Good. I really appreciate everyone paying attention. So, no other boo-boos, right? Okay, so now the thing that we do know is that despite all of this, there's still a lot of freedom. So there's actually freedom in well, in the various constants. Okay, and in particular, these lambdas are completely unrestricted so far. The only thing is that we know is that they must be the same between the ODEs. So the lambda on the first term, this one here, should be the same as the lambda in these terms. It's the only restriction so far. Now, moreover, right, because we have these restrictions, moreover, we can actually see that if the partial differential equation, in this case, the Poisson equation, is linear, okay, then solutions can be found by superposition. Okay, and again, let me highlight that if the equation is linear, which for the Poisson equation it is, then we can also find solutions by superposition of the various solutions that we find. And we know that we have considerable freedom in this case, in the various constants, right, in the lambda, as long as they are the same between the ordinary differential equations. And so, you know, we not only have solutions that are related of this form, in fact, we can construct solutions that are the superposition of separate solutions. So in this case, what we can even write is that phi as a function of xy is given by the sum, let's say, over I, and I can now write these ai, which is in front of it, and then I write big X, right? This is the function that only depends on X, which is I now label lambda I, xi, y, lambda I, y, like this. So what I'm trying to say here is that not only do I have a solution of this form, right, of a form like here, okay, of the form like this. But because the various lambdas are all solutions to a linear equation, then I can also add them up with an appropriate coefficient, right? So this is just a coefficient corresponding to the ith solution. So the ith, form of lambda I. And so in that case, well, we know what the final solution or how to find these, of course, are through the boundary condition. So for a particular boundary condition, so for example, it is f of x, at y equals to 0, then I know that I get f of x equals some sum of I, ai, x, lambda I, x, and then y, lambda I, evaluated at y equals to 0. Okay, so having specified, let's say on some boundary, in this case, this is y equals to 0, then I have that this sum of different functions of x, right, which are labeled by lambda I, and then given by some coefficient ai, must then match with f of x. So that's basically the premise, the concept of this separation of variables. And so the next step that I want to highlight is actually, no, let's continue for a little bit first. Is now to take a look at what are these functions x's and kind of what they produce. So the first thing that I want to take a look at is is actually jumping ahead and looking forward. So I hope that most people still remember, for example, two things, right? And so we recall that we can have a function. We can express that as a series. And so, for example, I can write f of x equals the sum for n from 0 to infinity. And here I could write some Taylor expansion to the power n, and then some function fn a, like this. Okay, and so these are then you can write, for example, here. I hope so. We've got the sine of x is just x minus x cubed over 3 faculty, right? Dot dot dot, and then we have also the cosine of x, and which is just 1 minus x squared over 2 faculty, dot dot dot, like this. Okay, so this is just an example of a series solution of a particular function. Now, I know most, if not all of you, also know that I could expand. So I can also expand a function. I can also expand a function as sums of sines and cosines. So if I expand a function as as an infinite series of sines and cosines, um, uh, what is the name that we've given it to this? Does anyone know? Okay, so Mr. Poon is saying Fourier series, and Alex, same thing, saying Fourier series. So indeed, right? So if I expand, so instead of this here is a Taylor series, right? Is a Taylor series. But if I now do it in terms of sines and cosines, then I get a so-called Fourier series. Uh, and this is actually something that we should, is something that should look familiar, because if I actually take a look at the form that we've gotten here, then we're more or less kind of hinting already at exactly this, right? Because we can express phi, our potential, in terms of periodic functions, cosine and sines, or at least in terms of exponentials. And so we're kind of left indeed with, already hinting at that we can do the expansion in terms of sines and cosines. And so that's what we're going to talk about now for a little bit, which are indeed the Fourier series. Okay, let's take a. This is actually a good time to take a 5-minute break. So we'll come back at 3:05, and in this 5 minutes, hopefully, I want you to at least remember or try to refresh your knowledge about Fourier series. Okay, and in particular, what I want to discuss are under which conditions, okay, or at least what I want you to think about is under which conditions can I expand a function as a Fourier series. Okay, I'll see everyone back in 5 minutes. Okay, welcome back. Let's hopefully we've all kind of frantically went back into our books and at least looked up. Does anyone know what the conditions are under which a particular fx can be expanded as a Fourier series? Okay, these are the so-called Dirichlet conditions. You don't have to memorize them. It's just something I wanted you to look up in your break. So Alex is saying piecewise continuous. I mean, you can formulate these conditions in various ways. In the way that I've written them down is, yes, the function must be periodic, single valued and continuous, except for a finite number of finite discontinuities. Finite number of optima within one single period, and that the integral over one period of the modulus of f of x must converge. I mean, these are just very technical, very mathematical. These are the conditions under which you are able to expand f of x as a Fourier series. Don't worry about it. It's just something I wanted to refresh your memory on. But in most realistic scenarios, you don't have to worry. The boundary conditions are not such that you cannot solve these. But I just wanted to remind everyone of these conditions. So, okay, let's take a look at the various properties, right? I mentioned that I can do these. I can do a Fourier decomposition, or I can do a Fourier series. And so one thing that we need to keep an eye out, and which makes our lives much easier, is if we consider symmetries. Okay. So if we consider symmetries, life will be much easier. So for example, I actually know that these cosines and sines have a particular symmetry. Okay? So for example, the sine function is odd or even. Odd indeed. Okay, now what does that mean? Well, if a function is odd, then f of minus x equals to minus f of x. Okay, now you must realize that these so-called odd functions, they cannot represent even functions. Okay, so not even using an infinite sum of odd functions can you represent an even function, because even if you have an infinite series of odd functions, they will all satisfy this property over here. And an even function, right, has the opposite, not opposite, but has a different property, namely that in this case the cosine function is even, and so in which case we simply have that f of minus x equals f of x. Now these, they cannot represent odd functions. Now, one thing that we do know is that any function can be written as a sum of an odd part plus an even part. Okay, and I can actually very simply do the following. I can say that f of x equals to a half of f of x plus f of minus x plus a half f of x minus f of minus x, like this, in such a way that I know that the first part is now the even contribution plus f, the odd contribution. And so it should be evident now that any function can be written as the sum of sines and cosine series. In other words, I can write f of x as in the following form: a naught plus 2, which is just a constant term, the sum of r from 1 to infinity ar cosine 2 pi r over L x plus br sine 2 pi r x over L. Okay, so any function f of x can now be written, well, given the Dirichlet conditions, can be written as an infinite sum of cosines and sines, right? Because an infinite series of cosines can represent even functions, the even part. The infinite sum of the sine functions can represent the odd. And so a sum of these, because any function can be written in even and odd form, any function can be written as a sum of sines and cosines. And so this is actually something that we will want to use. Now these ARs, okay, and these BRs are the so-called Fourier coefficients. Okay, so depending on the function f of x, these coefficients are different, and there's actually a relatively straightforward way of obtaining these so-called coefficients. So let's take a look at these Fourier coefficients. Fourier coefficients. And in particular, we're going to make use first of a particular orthogonality condition. Okay, so orthogonality conditions. And in particular, these are the following ones that I want to highlight. So if I integrate from some x0 plus x0 plus L, where L is the length of a period, then I can do sine of 2 pi Rx over L times cosine 2 pi Px over L dx equals to 0 for all R and P. Okay, so any value, any integer value for R and P, this is 0, right? We're integrating basically the integrand is an odd function times an even function, and integrated over a period. This equals to 0. Now, of course, this is different for if I have, instead of a mix between sines and cosines, I actually have something that could look like this, where now, again, I'm going from x0 to x0 plus L. And now let's consider if I have cosine 2 pi Rx over L plus, sorry, times, again, another cosine 2 pi px over L dx. And this here actually has the following properties. It actually has three values. L, if r equals to p equals to 0, right? So if r equals to 0 or p equals to 0, then it's a cosine of 0. It integrates to well, it's just ones, and so the integration of a constant is just the length of my integration limit. Now, if r equals p, but it's not 0, then this is actually a half L. So this is for r equals to p bigger than 0, and it's 0 if r is not equals to p. Similarly, I could also do this for the sine function. So from x0 plus L, and here if I integrate the sine function of 2 pi rx over L times the sine of 2 pi px over L dx equals to, in this case, we have two possibilities. So we have, this equals to a half L for r equals to p and 0 else. Okay, so these are simply the orthogonality conditions for the sine and cosine functions. And this is very useful because this allows us to select the actual numerical coefficients for the Fourier components can then be easily found. So in this case, if I want to find the Fourier components, okay, can be given by, and here I can do the following. I can write, if I take this function here on the bottom, and I integrate both the left hand and the right hand side by this factor times, let's say, a cosine or a sine, then by the orthogonality condition, most of the terms end up dropping out. And you're only left with one or two of these. So what do I mean by this? This is an example. So now I do the left and the right hand side. I say x naught from x naught plus L. So this is the left hand side, which is just f of x. And now I do it times cosine 2 pi px over L dx equals to a0 over 2, the integral from x naught plus L of the cosine 2 pi x over L dx. Okay, I think I'm running out of space, but let me try to fit this in. Plus the sum of r equals to 1 to infinity of AR, the integral of the cosine 2 pi Rx over L times the cosine of 2 pi Px over L dx plus the integral of r equals to 1 to infinity of BR, and then the integral from x naught to x naught plus L of the cosine, I'm just going to abbreviate this with C, 2 pi px over L times the sine of the same thing but with R. Now, if I look at the, orthogonality conditions, if I integrate a sine with a cosine, right, which is basically this term over here, then those all drop out. Okay? And in fact, if R equals to 0, then the only term that I get left with is these two terms here. And if r equals to p but not 0, so bigger than 0, I get the AR term over here. Okay, but of course, here I've written r is bigger than 1. So for the p equals to 0, I only get this term here. And then for p is bigger than 0, I get the AR term. So indeed, to be more precise here, is that I can get the Fourier coefficients. So in the case of p equals to 0, what do I get? I get that this is the integral from x naught plus L of f of x dx. Okay, because indeed here, if I look at this equation over here, if p equals to 0, so if this equals to 0, the cosine here on the left-hand side turns to 1. On the right-hand side, all the ARs and the BRs equal to 0, except for this one, A0 here. This here integrates this term here. Oops, I don't think you can see my pointer very well. What is that? Okay, let me do it this way. So this term over here is the only one that's left. So you get A naught. This here integrates to L. So I get A naught L over 2. And here, because this term equals to 1, I get f of x dx. And so indeed, if I go here, what do I get? I get this here equals to A naught over 2L. Similarly, if I now do P equals to R, okay, and this is bigger than 0, what do I get? I get that the integral from x naught plus L, f of x times the cosine of 2 pi Rx over L dx equals to ARL over 2. Okay, because if we look back here, if in this case R equals to P, then this term here goes, well, this is only for P equals to 0, it goes away, and here, this term over here, R equals to P, so I get this here, then integrates to 1/2 over L, right, for R equals to P is bigger than 0, and so here I get ARL over 2. And that's exactly this here. And so once I know, okay, let's go back to this function here. So once I know that I can write f of x equals to some Fourier series, then I can find all the Fourier components individually, all the individual ARs. I can find them by simply integrating the f of x with respect to cosine 2 pi Rx over L, okay, over a particular period. And that will then give me AR here. So AR here is just 2 over L times this thing over here. So I need to do an integral, but it's an integral with respect to a cosine. Okay, now similarly, I could get the odd coefficients. So these are the even coefficients. The odd coefficients are simply given by, so here the odd coefficients are given by the following: x naught plus L, f of x, and these are the sine, 2 pi Rx over L, and that gives me BR over 2L. Okay, so by doing two integrals, technically 3 integrals, I can get A naught, I can get the individual ARs, and I can get the individual BRs. And once I have those, I simply plug them into this series that I've seen over here. So this series over here at the bottom, and I have a series solution of this f of x. Right? I have a series decomposition of this a over of this f of x. Now, we can actually take a look at a particular example. Again, I'm going through this quite quickly because I do assume that you have all at least seen the Fourier theory and also how to get these Fourier coefficients. But nevertheless, let me show you a particular example. Okay, let's take a look at a particular example of how to get the Fourier coefficients. So here is an example, and what I want to do is a so-called square wave. Square wave. So how does a square wave look like? Let me try to use my superior drawing abilities to draw you a square wave. Okay, I already started off quite badly by drawing the axis in. Okay, here we go. And I use green and I use the dash like this. Okay, so a square wave will look something like this. Oops. Okay, back. Here we go. So let's see if we can do a Fourier decomposition of a so-called square wave. And let's make our lives a little bit easier. So here we can do this point over here is 0, and let's do one little cycle later here. This here, okay. This here is just minus L over 2, and this point here is L over 2. Okay, and so functionally I can write f of x equals to minus 1 plus 1, and this is for minus a half L x to 0, and here I've got 0 x and minus a half. So this would be the functional form of a so-called square wave. Okay, so if I was asked in a particular situation like this, I get a square wave, and then okay, how do I represent the Fourier series? Of course, you can write down the Fourier series first, which is simply to the Fourier series. So in this case, in full, is just again f of x equals to, and let me just show you the formula that I'm looking for. So this one here at the bottom, that's my starting point. So it's a over 0 by 2, and then the infinite sum of r equals to 1 to infinity of ar. Let's see, how did I normalize this? I normalized this. Okay, just ar cosine br. Okay. Ar cosine 2 pi r x over L plus br sine 2 pi r x over L. Okay, like this. So this is my full Fourier series, and in order to get the coefficients, I simply just need to do the integral of f of x here. So this f of x here, I need to do the integral either with respect to cosine to get the ARs, or with respect to sines to get the BRs. Now in this case, you can even check, is this function odd or even? Let me actually draw the axis better. So in this case, this square wave, is that an even or an odd function? At least it's word. It's not a weird function. Okay. Yes, indeed, it's an odd function. So I can find the coefficients, but I know that I only need the odd coefficients. I don't need the even coefficients. So the odd coefficients, which are labeled by B, are now given by so the only odd coefficients. I can now find them by just calculating what BR should be. So BR equals to, and this 2L, okay, 2 over L. And now here I do minus L over 2, L over 2 of f of x times sine 2 pi rx over L dx. Now sine f of x here on the top, you can see it's either -1 or +1. So in this case here, what do I get? You can do this integral in a fairly straightforward manner. I'm not going to do this all out here, but here you can actually write this to be 2 over pi r 1 minus 1 to the power r, this. Okay, in other words, if you explicitly evaluate this, then f of x is simply given by 4 over pi sine kx, okay, plus 1/3 sine 3kx plus, let's see, 1 over 5 sine 5kx, and so on and so on. Okay, where in this case I've just added a specific kind of, I relabeled it r in terms of, well, this 2 pi over r, 2 pi r over L, relabeled it as k. Okay, so I can write this as an infinite series then. So this is a way to get the so-called Fourier coefficients. And so, why did I go so painstakingly try to explain the Fourier series? Is because we now know that, or we can hint at, that we need to use for the coefficients over here in our separation of variables, that I've got all of these infinite sums of x's and y's, but because they are we've seen that the ODEs that govern them actually give me cosines and sines, or at least hyperbolic cosines and sines, and so it's something that I should be able, and we'll make it explicit after the break, that we can we need Fourier series to express our end result. So I think this is a good time to take a break. After the break, we're actually going to take a look at how to apply, Fourier series in order to get solutions in Cartesian coordinates using the separation of variable methods. Okay, so let's take a in this case 6-minute break. Let's come back at 3:40 before we pick up. Okay, I'll see you guys in a bit. Okay, let's get back to things. So I see that there's a question from Alex. So Alex is asking whether I can explain L in this case, so capital L, because in the previous course there's no factor of 2 inside the sine and the cosines. So L in this case is just the length of a full period. Okay, and this is just a convenient way to write the so that x, you can take x from integrating from 0 to L or from x naught to L. So L is here is simply just to specify what is the length of a full period. So it's simply all just convenient ways to do normalization. Okay, and the same thing for the factors of 2. Just the only thing you have to just be careful is making sure that you're keeping track of exactly what is the length of a period, and then even things like factors of 2, just do them by hand just to see if you can recover the right thing. Okay, so don't be alarmed too much by this L. I could have simply not considered L and just but then I needed to specify, okay, if I integrate x from particular values, that I'm actually spanning a particular period. Okay, does that answer your question, Alex? Excellent. Okay, good. So let's now take the remainder of this class to take an actual look at an actual example of combining all the pieces of information that we have now. So the first one is, of course, that we can do the separation of variables in such a way that I have as my solutions, I have sines and cosines or exponential functions. So that's the first piece of information. And then the second piece of information is how to write functions as Fourier series, and in particular how to get these so-called Fourier coefficients. So let's take a look now, and the particular example that I want to do is a rather simplified example. So just okay. So this is again another example, and this is for the separation of variables. Okay. And in particular, the example that I want to study with you is the following. So I'm going to draw a little box like this. Okay, and let me put some, okay, this is a little bit unfortunate. Let me make them a little bit more symmetric. So this and this. Okay, this helps a little. And let me lay down the axis in a particular way as well. So let's call this Y, and let's call this X. Okay, and the example is that the top and the bottom are two infinitely long grounded metal plates. In this case, let's call this phi equals to 0 for this one and this one. And then here I've got two plates that are kept at a particular potential. Okay, actually I drew this a little bit. Let's see which example. Okay, let me do it in a better way because the example that I prepared, Y is not here. Okay, let's shift things a little. And let's put things here. Okay, this is a slightly better representation. Let's see, let's move this out a little. Here we go. Beautiful. Gorgeous. Okay, so the scenario is so two infinitely long grounded plates, okay, at y equals to 0 and y equals to a. And then I have two, again, infinitely long strips, plate strips, doesn't matter, at phi equals to phi 0, at x equals to minus b or b. Oh, crap. Okay. This should be done. Okay. I should just delete it. I completely laid out the thing wrong. Okay. Now let's draw the axis better. So the axis should be actually here. Okay. So in this case, the axis, this is the y-axis, and this is the x-axis. Okay. And let me move this a little bit out of the way. Okay. Much better axis. Okay. And so in this case, I have, I have four walls that have a specific condition. Okay, so in this case here, this is phi equals to 0, and phi equals to phi naught at the two, at x equals minus b and b, and at phi equals to 0 at y equals to 0 and y equals to a. So here, my goal, or the thing that I want to do is, I first, well, the thing I want to do is solve, right, just the Laplace equation under a particular set of boundary conditions. So these are the so-called boundary conditions are the following. 1, phi equals to 0 and y equals to 0. 2, phi equals to 0 and y equals to a. 3, phi equals to phi naught and x equals to b. And 4, phi equals to phi 0 and x equals to minus b. And finally, I know that my general solution is given by phi as a function of xy equals to a e to the kx plus b e to the minus kx c sine ky plus d cosine ky. Okay, now just for convenience in this case, I've chosen the x to be just the exponential functions, and then the y chosen to be periodic functions. This is something that you'll learn by looking at a situation. You'll learn to recognize what is the easiest thing to do. But in general, and this is something that I can go all the way back. Oops, no, that's the stick figure. I can go all the way back here. So I do have the freedom to write things in terms of a hyperbolic, cosine, and sine, and a regular cosine or cosine, or in terms of complex exponentials or simple exponentials. So that's just my choice, because in the end, all that I care about is that they adhere to these two ordinary differential equations. And so in order to make my life simple, I've chosen it to be this form. Again, it's something that when you do exercises like this, you will end up recognizing like what is the easiest thing to do. Okay, so we've now completely set up the problem. And all that I need to do now is to use the general form, but make sure I adhere to the so-called boundary conditions. Again, the general form here stems from expressing or solving the Poisson equation, but assuming that I can do separation of variables. So this is big X as a function of small x, and this is big Y as a function of small y. Okay, so we've laid out the entire problem. So mathematically, we solved the Laplace equation. I've laid out my boundary conditions. I get my solution for the Laplace equation in Cartesian coordinates. And now all I need to do is match the boundary conditions in such a way, and then I should be good to go. So let's actually see, let's do that. So again, we're still at the example. And so here, let's take a look at boundary condition 3 plus 4, right? 3 and 4. So one thing that I know is that minus x equals to phi plus x. Okay. So if I do this, and if I look at this general form, so if I substitute minus x and plus x here, then I should reach the consensus that A equals to B. Okay, so the coefficients here, in this case, if I do minus and plus, if I flip them, then I should get the same answer. So in this case, A equals to B. Okay, and so this then leads to my solution, xy equals to A. I can now take A out, e to the kx plus e to the minus kx. This times y. Okay, y as a function of small y. Again, I don't explicitly write out, and that's just a sine cosine. And so in this case here, I can actually equate this to be 2a hyperbolic cosine of kx. And again, big Y as a function of small y. Now, I can outline this even further. I can just call this the hyperbolic cosine of kx, and now I write c sine ky plus d cosine ky. And so in which case this 2a I've just reabsorbed into c and d. So originally I had c and d here, and now I reabsorb the a or 2a into c and d. So these c's are slightly different from the c's before. But it doesn't matter, right? These are just constants that I need to do. Okay, so now we've used two boundary conditions. And in which case, I know that I've got two left. So let's take a look at boundary condition number 1. Okay, so what is boundary condition number 1? Boundary condition 1 is that phi equals to 0 for y equals to 0. So if I now take a look at this form and I substitute y equals to 0 in here and here, what do I get? Well, cosine is not 0, whereas the sine is 0. But overall, phi needs to be 0. So I know that the cosine contribution must drop out, must disappear. And so here I know that d must equal to 0. Similarly, if I look at the boundary condition number 2, okay, which here states that phi equals to 0 and y equals to a. Okay, we already established that d equals to 0. So I now know that sine k, in this case, this is a here. Okay. Okay, let me write it out. Actually, it's a little bit easier if I write it out. So I know that my c sine ka equals to 0. Okay, and so under which condition is sine ka equals to 0? So in other words, under which condition for k does sine equals to 0? Here I now know that ka equals to an integer of pi. Okay, so in this case, n is an integer. And so now what I have is the following, right? N is, sorry, any integer or any positive integer because we're looking at Fourier series. And so now that I've got this, I know that d equals to 0. I know that k equals to, any integer. So my intermediate solution, right, having applied boundary conditions 3, 4, 1, and 2, my intermediate solution is that phi x y equals to c, and I haven't determined c yet, is the hyperbolic cosine of n pi x over a times sine n pi y over a, right? Remember, in this case, ka equals n pi. And so I've got k here, and I've got k here. Again, d equals to 0. So this is my is a particular solution that works. Again, for where n is any integer. Now I know, again, we've said this before, right? The Poisson equation is a linear equation, and so I can have a superposition of all the solutions is also a solution, and so I can superpose. Oops. So now I can superpose all possible solutions, right? So of n in such a way that I get the following. So phi of x and y equals to now the infinite sum of Cn. Now I've labeled all the C's, right? Here I just have C, but different n's, right? Different solutions for n could come with a different constant in front, a different coefficient. So I labeled them with n, and then I got cosine, hyperbolic cosine of n pi x over a, and then the regular sine n pi x over a. Okay, now if you look back here, then even though I've used boundary conditions 3 and 4, I've only used a fraction. I haven't used the full information in boundary conditions 3 and 4 because I've only specified that this is phi of minus x equals phi of x. And so I still have boundary condition 3 that I'm allowed to use. So here, I take this form now, which is a superposition of the hyperbolic cosines and the sines, and now I look at boundary condition 3, which in this case states that phi b any y equals to phi naught. And so in this case, what do I have? I have that this here equals to the infinite sum n from 1 to infinity Cn, and this is the hyperbolic cosine of now n pi over a times b, right? Because I now have inserted b in x times sine n pi over a y. So now bear in mind that this here is just phi, let's say just some function, let's not call it phi, let's call it g, right? So this is just a function of y. And so what do I have? I have now that a constant phi naught here is some infinite, series of sines of y, right? And so what I've effectively done is I've now written this g of y, right, which is just phi b comma y, is again just a Fourier, it's just a Fourier expansion. So I get a constant equals to a Fourier expansion where the coefficients, right? So effectively, these are now my coefficients because they do not depend on y anymore. But these Cn remain undetermined. And that's going to be the next task. But we've seen before, when we looked at the Fourier, how to get the Fourier coefficients here, that, we take a particular function f of x, we multiply either by cosine or sine in order to get, the so-called Fourier coefficients. And we can do exactly the same here. So in this case, what do I do? Well, on the left-hand side, now effectively the f of x here is just a constant, is phi 0, but I can now do the integral from 0 to a. Okay, this is this is over one period. So here is phi naught, and now I do the sine because I'm cheating. I know that here I only have sines, so I don't need to bother with cosines because of the odd and even symmetries. So I do sine, and now I do some, in this case, n pi y over a dy. And so here now this now equals to the actual coefficients, but the coefficients themselves is just a over 2 cn, and now the hyperbolic cosine of n pi b over a. Again, remember that the cn hyperbolic cosine is the actual coefficient. So if I go back to this over here, then indeed I get something that looks like L, which is the length, in this case that's A, over 2 AR or BR over here. In this case, BR or AR is just Cn hyperbolic cosine n pi B over A. So this now gives us the final tools. Now, bear in mind, of course, this n here and this n here is, okay, maybe to avoid confusion, let me make this m. And okay, it has stopped working again. Okay, now it's back home. Let me make this m, n, and n. Okay, just to avoid confusion with n. So indeed, if I multiply by m and I integrate this, then I'm only selecting out those for which m equals to n. Again, this is just the simple, how to get the Fourier components out. So let's take a look now. I can now do, I now know that Cn hyperbolic cosine of m pi b over 2 equals to 2 phi naught over a, the integral from 0 to a, and this is the sine of m pi y over a dy, which I now know is 2 phi naught over n pi 1 minus cosine m pi here. Okay, this is simply integrating the sine function over here. And so indeed, this here now equals to either 0 for even m, or it's 4 phi naught over n pi for odd m. And now I can put all of this together because I now know the Cn is just given by the following. It's just given by, let's see, 4 phi naught over n pi 1 over hyperbolic cosine n pi b over 2 for odd m. And so now the final solutions, okay, now that I've got Cn, I simply plug it into this form over here, right? I have Cn over here now. And then I'm more or less done. So now I plug everything in. So now the final solution, is now phi xy equals to 4 phi naught over pi, and the sum of n odd, okay? So just the odd n, 1 over n, and now I've got the hyperbolic cosine of n pi x over a divided by the hyperbolic cosine n pi b divided by a times the sine of n pi y over a. Like this. Okay, so this is now ends up being my final solution. And so if I go all the way back to this figure over here, so having set up my boundary conditions, okay, that I know phi has to be kept at a particular constants, left and right, and they have to be kept at 0 here at the top, then I can solve for the Poisson equation in the middle. I use all the boundary conditions, and I put this into the general form of the solutions. I consider all the boundary conditions one by one. I get something that looks like a Fourier expansion. And so I use my boundary conditions to find the Fourier coefficients, or the equivalent Fourier coefficients. And then I simply plug everything back in that I know for, in this case, Cn. And I plug it back into, actually, this should be y. I plug it back into this solution over here, the relevant Cn's, and I get, indeed, this solution out. Okay, so that brings me really to the end of this particular aspect. So we've looked at how to solve the Poisson equation, or the Laplace equation, in Cartesian coordinates, okay, in separation of variables. And so all that, you're really, your task that you need to do is you need to use the general solution, try to match the boundary conditions, but bear in mind that, I don't look at a single example, I look at all the possible examples. So you end up with a series solution, and then you need to find the coefficients of the Fourier, of more or less a Fourier decomposition. And so that's how you solve one in Cartesian coordinates. What we're going to do next lecture, and I'm just looking ahead. So in the next lecture, we're going to try to do the same thing, but in a different coordinate system, because when you know, not all examples are as simple and straightforward as boxes or infinitely long square tubes. Instead, sometimes we're talking about cylindrical symmetry, or we're looking at spherical symmetry. And so in the next lecture, which is going to be next week, we're going to take a look at how to do exactly the same, but using different symmetries. So in different coordinate systems, particularly in curvilinear coordinate systems. And what we'll find, and this is again looking forward, so instead of using Fourier series, right, which is intimately connected to the Cartesian coordinates, we actually find that we get a different series expansion. And so in this case, we get a series expansion for the spherical coordinates of the Legendre polynomials. And that's actually the point where we'll consider that in more detail. And in the cylindrical coordinates, we get the so-called Bessel functions. Okay, so that's something that we can look forward to going to the future. So this more or less ends of what I wanted to discuss today. Let me open up the floor to see if there are any questions about this. And again, afterwards, I'll turn off the recording for off-the-record questions as well. Okay, so let me open up the floor to see if there are any questions about this. I will say that the problem set that we're going to release today, and then the exercise class will again give you another example of going through step by step how to use the separation of variables and how to get the coefficients. So you get this example, but you also get an example in the exercise class that you can worked examples that you can follow, and then hopefully in the problem set you get to see you get to try this out for yourself. Okay, so there is a question from Ko Yi Choi, and the question is, do all these boundary conditions relate to the boundary conditions near the surface we have learned? So so for the time being, we typically specify the well, to make things easy, sometimes we just simply specify, okay, phi is a particular shape, particular distribution, and that's just to make your life a little bit easier. Now, when does it, these boundary conditions you've learned for the electromagnetic field, when does it become important? Is actually in the next block. So after the midterm, we're going to start discussing. Well, actually, it's technically slightly before the midterm we start talking about it, but after the midterm, in terms of kind of material, is when we start considering materials, right? So once we have materials, we need to know, okay, how does the boundary from one place to another, how does it differ? And so the boundary conditions will no longer be, the potential is of this form at this boundary. Instead, we're saying, okay, we're going to put one material next to or even inside the other material, and then you need to solve it. And so you then, an extra step is then you need to also first find what are the exact boundary conditions before you can solve the problem. So that's kind of, the moment when you really start using the electromagnetic boundary conditions is, when you have a little bit more complex situations where we have materials inside other materials. And yes, some of them do require you to take derivatives first. And so, these questions and then solving them especially in separation of variables, can become quite cumbersome, where you need to find solutions, you need to match the boundary conditions, but that may require you to take derivatives of the fields first, and so on and so on. Okay, so Zheng Ling is asking, why do we need to use a general solution to match boundary conditions? Can we just use one particular solution to match the boundary conditions? Say only use solutions n equals to 1. So here's the thing, okay? I want to remind everyone about the uniqueness theorem. If you can find a solution using only just one, right? You don't need to use a general. If you just find one solution, n equals to 1, that matches the boundary conditions, you're done. That's the only solution. Now, of course, when you go through the problem, and if you can find a solution, well, you can write it in a general form first. And if n equals 1 is the only one, then that will give you the right answer. But for me, honestly, it's absolutely correct if you say, okay, I recognize, right, these are exactly the same form. I don't need to consider writing it first out in a more general form first, doing the various integrals, showing that all these coefficients are 0. Instead, you say, okay, well, this solution here matches the boundary conditions, and by uniqueness theorem, I'm done. Good enough for me. Alex is asking, in this week's problem set, do we need to find the E field also inside the region where the image charge is situated? So no. So in the method of images, you do not consider the region of the image charges, right? So typically we have some conducting plane, and so the whole process of writing image charges is simply is to substitute this conducting plane, and therefore we cannot put image charges in the area where we're actually considering the solutions themselves. So no, the region of the image charge is typically not considered. So okay, I'll just ignore that. Are there any other questions? Okay, if you're not gonna specify which question, which part, it is very difficult for me to just know exactly what you're talking about. So Punchun Chi is asking in the homework, can we identify the boundary as a Faraday cage in the homework? I honestly don't know what you're talking about, so yeah, it is difficult. And like if a real charge is inside the boundary, then automatically E equals 0 outside Q2. I need to look up Q2, so maybe we can kind of do this kind of off the recording. So for the time being, let's just see if we have any questions regarding the lecture, and then I'll turn off the recording. We can talk a little bit about the problem set. And actually, one of the TAs is here. He should probably know a little bit more quickly what Q2 is. And by the way, which problem set are you talking about? It would also be nice if you said that. And then we can answer that. So let me see if there's any more questions about the lecture itself. Okay, going once. Second last slide. Okay. Second to last slide. This one. Oh, should that be an A? Yep. Done. Oh, I'll make it a little bit prettier. Okay. Thank you for spotting that. Okay. I'll leave the questions about the homework for afterwards. Okay. Last chance. Questions about the. Yeah. Okay. Fine. Fine. Okay. Here we go. Well done. Is that your question, Harry? That should be an A. All M in it. Yeah, you need to. Okay, so the thing is for. I mean, you're right. I didn't want to use M. I didn't want to use the N because that is typically used as a series, whereas this is a particular M, right? So that's why I wrote M here. But yeah, sometimes I forget and I just keep writing M. And here, this is M. Like this. But you're right. I mean, you have to make sure that. But yeah, so here I'm talking about a specific M, and there it's in the series. So I wanted to make sure that I don't confuse those two. Okay, last chance. Going once, going twice. Stop the recording.